Hello everyone, I hope all you are doing very good in your life. Today in this video we will try to cover bending beams and expression for bending moment. These two important topics we will cover in this video. One is bending beams, which may come for definition, and expression for bending beams is a derivation which may come for 8 marks. So both are very important in this video. Please stay connected. Before I start the video, I would like to request you to subscribe to my channel and press the bell icon. With this, let's roll the intro. Bending of beams. Beam is defined as a rod, or you can also say that a bar of uniform cross section whose length is very large than its thickness is nothing but we call it as a beam. Beam may be considered as made up of large number of thin planes, horizontal layers placed one over than other, as we can see in this diagram. So this is nothing but we call it as a beam. So once a beam or a bar bent, then the outer layer get elongated. At the same time, the lower layer will get contracted. But at the layer which is present in the middle of these two layers, neither going to be contracted or not going to be elongated. This type of layer we call it as a neutral layer or a surface. In the next topic, neutral axis means this is an axis of a cross-section beam or a shaft, we can say, where there is no longitudinal stress or strain. This is nothing but we call it as a neutral axis. In the next topic, bending moment of a beam is defined as the total moment of the force acting on the upper and lower layer or a surface of the beam. This is nothing but we call it as a bending moment of a beam. In the next topic, we will see the expression for bending of moment in terms of momentum of inertia. Let us consider beam ABCD of a length L. AD is the fixed at the one end, where W is attached at another end. W is the weight which is attached at the plane BC. When we look at this plane, we can easily observe AB is the plane which is get elongated and DC is the plane which is get contracted, where at the same time EF is the plane which is neither going to be elongated or neither going to be contracted. So this is what we call it as neutral axis. In the next step of the derivation, we can see the bending moment of a beam is equal to the restoring couple acting on the beam. So let us consider a small portion of a beam which we take it as P, B, C, Q, which get curved due to where we applied W as a weight, or we can also say that a load. We can divide three layers PB, QC and GF as an outer, inner and neutral filaments respectively, and O be the center and R be the radius of the curvature of an arc. Neutral filament GF and R be the distance of a PB from GF. So we can say the neutral filament or the length of the filament GF is equals to R into theta. Theta is the angle sustained by GF at O. Now we can find out the length of an outer filament with the help of GF. So PB is equals to capital R plus small r into theta. Now we are going to see the definition for linear strain or longitudinal strain, where it means that change in length by original length, nothing but increase in length by initial length. Initial length of the curve is r theta and change of the length is capital R plus small r into theta minus capital R into theta. If we solve it, we got it small r by capital R. Take it as equation number 1. We can see the change in length and all. We can use Young's modulus, where y is equals to linear stress by linear strain. So stress by strain is nothing but which is related to the length, so we call it as Young's modulus. Therefore the longitudinal stress is nothing but y into linear strain. The linear strain, we already derived the equation number 1, r small r by capital R. So we can write it as capital Y into small r by capital R. Take it as equation number 2. And I hope you know what you mean by longitudinal stress. Stress means force by per unit area. So F by A. Take it as equation number 3. So by using equation number 3 and 2, we can write it as F by A is equals to Y into small r by capital R. We rearrange the equation, we get capital F is equals to capital Y into A into R divided by capital R. We can say that force on a neutral axis is equals to force into its distance from its neutral axis. So F into small r. So capital Y into small a into small r divided by capital R. This is an equation we got it when we considered only end of the beam. Now let us consider this equation for an entire beam. Then we can write the equation as summation capital Y A small r square divided by capital R. So the ultimate equation is capital Y capital R into summation of A into R square. Take it as equation number 4. Moment of inertia of a body which is given by summation m into r square, where summation into m is the mass of the body. Similarly, summation A into r square is called geometric moment of inertia, that is we call it as Ig. So Ig we can write it as summation A into r square, that is nothing but A into k square. A is the area of the cross section of the beam and k is the radius from its neutral axis. Therefore the moment of the force, that is equals to capital Y by R Ig, or bending moment we can also write it as capital Y by capital R into Ig. So Ig means moment of inertia. In this derivation, either we can select rectangular cross-sectional area or circular cross-sectional area. For a rectangular cross-sectional area, we have different formula, and circular cross-sectional area we have different formula, as we can mention in this derivation. This is the end of the derivation, and this derivation may come for 8 marks. That's it for today guys. I hope you got to know whatever we try to explain in this video. If you have any queries related to this video, you can comment in the comment section. Before that, subscribe to my channel and share with your friend.